So the first announcement is that nothing I say today will be on this evening's exam. Everything from today will be on the next exam. So don't worry about that. Don't worry about today's lecture for the exam. There's one other announcement I need to make, though, and that is that it's come to my attention that there are a number of exams from last semester that have been released. Apparently there have been emails going around with the exams attached. It clearly says in the syllabus that copying or having or downloading old exams is an academic integrity violation. And it's true. Not to put too fine a point on it, it's cheating. When you open them, they have big copyright on them. And so you're not meant to have these. The problem is some of you will have them and some of you won't. The next problem is that means I have to rewrite the next exam with new questions. It also means that when I write the new questions, they may not be as clear, as well honed as the old questions. And what's more is I'll be angry, and so I will write questions that get harder and harder. And by the end, I'll have questions that will make your eyes bleed. And so I don't know how to approach this. If you have these emails and you haven't opened them yet, I'd ask you not to open them. If you have these emails and you can follow the chain, I'd appreciate knowing the chain, because I really want to get back to the genesis of this. I want to know where it started, because this is not a fair way. It's not fair to those people who don't open these quizzes. Yeah, these exams. Yes.
The people who have it are going to suck my curve up.
Right, exactly. The people who have it are going to suck your curve up. That's right. And on the other hand, maybe they're not as bright as they think. I'm not sure. So it's right. I mean, there's a serious academic issue with this. It's a serious question of fairness. And I don't really know how to address it. And I've always turned the exams back in good faith because I think they're really important study tools. They're really important for studying for the final. And I don't know how else to draw a thread through the course when you study for the final without having access to these exams. And so it's a bit of a frustration on my part. Yes?
So the first exam, is it rewritten, or is it the same that people are not?
It's not the same.
Okay.
I didn't find out till yesterday, after the exam had gone to the printers. I can confidently say it's not the same exam, but I can confidently say it ain't entirely different either. So, and there's the crux of the problem. So we'll go from there. I'm not sure what processes will change, but something will probably have to be done differently. So where are we headed today? So for today, we're going to start into this idea of the nervous system as a machine. And all I really want to do with today's discussion is to impress upon you that the nervous system isn't anything different from the rest of biology, that it follows the same physical and chemical principles of all of biology. And the idea that the nervous system is a machine is a fairly recent concept. Probably didn't come even into the beginnings of its ideas until about 1850. And so over the last 150, 160, 170 years, we've now begun to see how the nervous system functions. We've begun to test with hypothesis testing how it works. And we've made enormous progress. We've made enormous progress in understanding how the brain functions. Now, it's going to be interesting as time goes on, because I suspect that in your lifetime, we may be able to completely understand how the brain works. We may be able to understand how all the connections function and how consciousness arises from this blob of jello in your brain case. I think that's a remarkable thing to be able to do. I think it's a remarkably human thing. I think the ability to look inward into our brains and think about how we function as a biological machine is just a kind of philosophical question equivalent to the Hubble telescope looking back 1 billion or 14 billion years in time. I find these things sort of a human things to do. Other animals can't do these things. And the curiosity and the trying to understand and the creativity of doing this, to my mind, of understanding the nervous system as a machine, is one of the true accomplishments of humanity and will be one of the true accomplishments of all of humanity. In the process of doing this, we'll probably find out ways to cure any number of diseases. We're probably going to be able to find out ways to thwart aging and Alzheimer's and multiple sclerosis and any number of diseases. But as we begin to understand more and more about the chemistry of the brain and how the neurochemistry of the brain can be altered, we're going to be able to alter people's behavior. We can even see some of that now. I mean, you all know what will happen by the end of the semester. You will have not studied as much as you should have. You won't be up as well on time. You're in a time crunch. You're a little panicked, but you think it'll be all right. Somebody out there has some Adderall. And so you take some Adderall, you focus a little better, you do a little better on the exam, and so you're modifying your behavior. And so where do we put the limits to this as to what's ethical and what's not ethical? And where do we put the limits to giving people drugs to make them behave better because we don't like the way they're dealing with their society? I don't know the answer to this, but we are crossing those thresholds now. And as time goes on, in your lifetime, we're going to cross many more thresholds. And in a democracy, how we think about these things, how we approach these things, how we deal with them are up to you and the people around you. And I think it's important to learn about nervous systems and how they function and what they mean and the ethics of it so that we can make rational decisions about what's fitting and proper and what's not. And so this all starts with the idea of the nervous system as a machine, and we can think about the nervous system as a machine as a three-box model. And the three-box model is one that any computer scientist will recognize. It simply says data in, analysis, data out. And our brains work, our nervous systems work much in the same way. But we can now impose upon this three-box model some biological concepts and definitions. We'll see that our nervous systems are divided into three major regions. There's a peripheral nervous system, and this portion of the peripheral nervous system will carry information toward the central nervous system. The central nervous system is composed of the brain and spinal cord. But all the information coming into the brain and spinal cord is going to come from the periphery. And so there are going to be neurons that will be carrying information toward the brain and spinal cord, and we call these sensory afferents. Afferent comes from the Latin, it means to carry toward. So all the information you're receiving about the world around you is coming in through these sensory afferents. That information then is delivered to the central nervous system, which is the brain and the spinal cord. Then in the brain and the spinal cord, there are enormous numbers of connections. There are something like 100 billion nerve cells and like 1 trillion or 10 trillion connections. And these connections then lead to the analysis in ways we don't really understand. In biology, we'll call this integration. So we're taking sensory information in, we're integrating that sensory information to make sense of it. We decide to do something, and then we send signals back out from the central nervous system into the periphery. We'll send those signals out to muscle or gland so you can do something. And so in that point, we can think about these as motor efferents. And again, the term efferent comes from the Latin. It means to carry away. So we'll walk through that as some generalized ideas about the nervous system as a machine, and I'll give you a short history of where all that started. And then I want to spend a little bit of time on sensory transduction. We really don't have time in here to get into the nuts and bolts of how the sensory systems work. It's unfortunate we just don't have time. There are other courses. The cellular neurobiology course that's taught here has a great series of lectures on sensory transduction, and sensory processing, all for vision and hearing and taste and smell. All of those are covered. And it's a wonderful course, and I'll encourage you to take it there. But we're just going to go through some very fundamental ideas here. Fundamental idea I want to drive home here is to simply say that whenever we're talking about the nervous system as a machine, and we have to recognize the energy in the world around us, what's required is to change energy forms. So if you think about it for a minute, you recognize that everything you know in the world around you comes in from electromagnetic radiation, which for us is light. It comes from mechanical information, which we'll see as sound, also touch. So when you reach out and touch something, you're deforming nerve endings, and so that's a mechanical change. And finally, you know a lot about the world around you from taste and smell, and that'll be chemical. But in all cases, you can think about the energy of electromagnetic radiation, mechanical energy of movement, or the energy of the chemical structure as being a kind of energy in the outside world. But for the nervous system to make any sense of it, it has to change the form of energy. And the way it changes the form of energy is it moves ions across phospholipid bilayers. So the very beginnings of understanding the world around us all starts with a change in ion movement, ion flux across membranes. And that's what I really want you to think about in terms of transduction. And we'll talk about some special cases here of electromagnetic and mechanical inputs. And then finally, if there's time, we'll talk a little bit about the neuron doctrine. And the neuron doctrine is a fundamental idea of neurobiology. And it came about in the early part of the 20th century, the late part of the 19th century, and it now is accepted as gospel. And it says the neuron is the fundamental structural and functional unit of the nervous system. But at the time, there was an enormous argument that went on about whether it was the individual neurons or whether it was a gamish of all these neurons attached one to the other by cytoplasmic bridges. Now, in the early part of the 20th century, that argument was sorted out, and that really began the whole process of understanding cellular neurobiology and the idea of the neuron as being the basic unit. And we'll talk a little bit about that. But let's begin here on this panel by labeling the nervous system as a machine. And in its simplest form, we can describe it as this three-box model, which says input, it says analysis, and it says output. Well, this is, as we said earlier, a concept that any computer programmer would recognize. You put something in, then you analyze information, and then you have an output. But when we think about it biologically, we can still maintain the three-box model. But we begin with sensory input. So the sensory input could be vision, it could be hearing, it could be smell. And the example that I often use in this is imagine one of our ancestors standing out on the Serengeti plain, and there's a lion coming toward them. And so there's sensory input. There's vision of the lion. There's perhaps hearing the lion. If the lion's really close, there may be smell. So there are all this sensory input. And that sensory input now is taken into this integrative unit. The integrative unit, which we'll see in a minute, is the brain and spinal cord. This integrative unit then takes all the sensory input and begins to make sense out of it. So in the case of the lion, it says, how close is the lion? Does the lion look hungry? Is the lion walking toward me? Is it walking away from me? Is the lion within striking distance? So there's all this integration and analysis. And then, after the analysis is done, then the integrative unit must make a decision and send information out to do something, which is output. So of course, in the lion story, the person sees the lion, the person recognizes the lion, and the recognition occurs in the integrative unit. The integrative unit then says, is there danger or not? And if there's danger, it says, run away. And so that's these three-box models. Now, the complexity of the integration is astonishing, and how we make these judgments is completely unknown. But fundamentally, it's sensory in, integration, and output. And in the nervous system, we can describe these as sensory afferents. And these sensory afferents are largely found in the peripheral nervous system. Now, if you get into the weeds of this and you take an anatomy course, you'll begin to recognize that particularly the retina is an outpocketing of the brain, so it's really not in the periphery. But we can think about it as being in the periphery and carrying information toward the integrative or analytic unit, the integrative or analytic unit here, is going to be the brain and spinal cord. In our parlance of the nervous system, we call the brain and the spinal cord the central nervous system. And then finally, out here, this is again motor efferents. This is again in the peripheral nervous system. So fundamentally what we're saying is that sensory information is being carried toward the central nervous system. So on the sensory side of this, we have sensory afferents carrying information to the central processing center, which we call the brain and spinal cord. Then once the brain and spinal cord have made a decision as to what to do, once they've analyzed, the neurons here have analyzed what's going on in the world, they'll then formulate a plan and then execute that plan by sending information out to muscle and glands through the motor efferents. Now, one of the ways I keep this afferent and efferent separate is the term efferent. It has the same root as the verb effect, meaning to bring about. So these motor efferents are bringing about a change. They're bringing out about movement. So when you think efferent, think muscle or glands and movement. When you think afferent, think about information being carried toward the central nervous system. When you think about efferents, think about information being carried away from the central nervous system to go out to muscle to do something. So those are the fundamental ideas of how we think about the nervous system as a machine. We can break it down into boxes. Now, we have spent the last 100 and some years sorting out how sensory afferents carry information, how they transduce the information. We've spent a lot of time trying to figure out how the information is integrated in the central nervous system. And we spent a lot of time trying to understand how the muscles are moved with their connections to the neurons. And we'll talk a lot about that. But much of this remains mysterious, and we don't know even yet how these things function. But where this stuff all started, and there's sort of an inflection point in history that as neurobiologists we point to, and it's probably a bit of an exaggeration. There were probably a number of philosophical changes going on at the time. But we think about the inflection point as being a case of an unfortunate industrial accident. There was a fellow named Phineas Gage, and Phineas Gage was a foreman on a gang working in Vermont. And his job was basically to go out and blow up rocks. And the reason he was supposed to go blow up rocks is he was employed by a railroad company, and they were laying railroad bed. And this is a big thing this is 1848, and this is an enormous thing going on in the United States, throughout the world really, in the middle part of the 19th century. And what they were doing is they were connecting the entire country by railroad lines. Because in the early part of the 19th century, they'd figured out how to make steam engines, and then someone figured out how to take a steam engine, attach it to wheels, and move those wheels with a reciprocating piston and put those wheels on steel rails. Now, it all worked fine, but the problem is when you put a steam engine that's that heavy on steel rails with steel wheels, you can't go up much of a hill. There just isn't enough friction. And so that meant that they needed another innovation. And one of the innovations that came about at that time was surveying. They needed to be able to survey the land and then go out into the land and change the rate of rise of various hills. And that's what Phineas Gage was doing. He was working in Vermont. And if you've ever been to Vermont, you know that it's really hilly. And not only is it really hilly, but it's also really rocky. There's a lot of granite up there. And so his job was to go out and blow up rocks and basically make a roadbed. And so the way that was done in the mid part of the 19th century is one person would go out with a great steel rod and a hammer, and it was called a star drill, and they would basically hit the rock, turn it, hit the rock, turn it, and they would drill this in this laborious way. They would drill down into the rock, maybe 8 inches or a foot. And then the next person came along and put into that hole in the rock black powder. Now, at this point, there was no such thing as dynamite. Dynamite came much later. It was a safety innovation. All they had was black powder, and it was really pretty dangerous to work with. So what they would do is they would put black powder into the hole, and then they'd lay a fuse into the black powder, and then on top of the black powder, they would take sand. And they'd pour the sand into the hole, and then they would take a rod, usually a rod just about this size, about 1.5 inches, 1.25 inches in diameter, about 4 feet long, and they would come up to the hole, and they would then have the sand in the hole, and they would tamp the sand down into the hole. By doing that, when they lit the fuse and exploded the black powder, the force of the explosion was directed down into the rock and break up the rock. Well, that was Phineas Gage's job. He was supposed to drill the holes, put in the powder. And apparently what he'd done is he'd drilled the hole, he'd put in the powder, but he'd forgotten that he hadn't put in the sand. And so he had this steel rod and he had this granite rock, and he went tink, 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 tink. He struck a spark. When he struck the spark, it ignited the black powder. When it ignited the black powder, it drove the rod up through his left cheek and out the right side of his head. Or maybe it was the other way, but it went up through his cheek and out the top of his head. Phineas Gage drops like a stone. Ka-thunk. Everybody thought he was dead. But then he sat up and he started talking to people. And then they gathered together a cart, and they brought a cart in, and they hauled him off to the local inn. He was sitting on the porch when the doctor arrived and put up his head and said, "I'm your business today, Doc." And so he was conscious, and he was doing pretty well. Then the doctor got there, and the doctor started taking good notes. And one of the first descriptions was that Phineas was doing pretty well. He was coherent, a little disoriented, but pretty coherent. And then suddenly he leaned over, and he got sick, and he vomited, and a half a teacup of brain came out of the hole in the top of his head. Now, again, I don't know how this guy lived, but they basically took him into the inn, put him to bed, and then the doctor would come back every day, and he kept very, very meticulous notes on Phineas Gage's progress. And he talks initially about a digital exam. Now, a digital exam in 1848 is different than a digital exam today. In 1848, he took his fingers and put them down his brain and started feeling around. And apparently, he was a pretty good anatomist because he predicted the parts of the brain that were going to be damaged from just sticking his finger in there. And then there's another frame about a week or two later where the doctor talks about mold growing out of Phineas Gage's head. But remarkably enough, Phineas Gage recovers. But if he'd recovered completely, there wouldn't be a story. The story is he's never quite the same again, where he's described as this hard-working and industrious man who got along with his family, got along with fellow workers, took instructions well. After that, he can't plan anything. You can't depend on him for anything. He isn't the upstanding Victorian fellow he was before. Now, there's probably a lot of exaggeration to that, but nonetheless, it looks like Phineas Gage at this point can't function the way he did before. There was a clear change in Phineas. Phineas's personality was not the same. And so that was the first indication that our brain is telling us who we are, that we are who we are because of our brain. It's not because of our soul, it's because of our brain. That's a philosophical change. Now, the story goes on. Phineas Gage can't get along with his family. He leaves his family, he goes to South America, he works in Chile for a while on a stagecoach. He drives stagecoach back and forth. But he continues to get sicker. We now know probably what happened, that with that kind of massive brain injury, there was an attempt on his nervous system to rewire that brain, and in the process, there was probably a lot of rewiring, and he became an epileptic. So he periodically had these seizures. But his mother and his sister had moved to San Francisco. So he took a boat from Chile, where he was working, back to San Francisco and settled in with them. But after about a year there, he died. He died of an epileptic seizure. And so they buried him in San Francisco. And then word got east, back to the doctor, that Phineas had died. And the doctor's response was, "I want the head." And so they disinterred Phineas, chopped off his head, and sent the head back. And to this day, the head is in a museum in Boston. And about 15 years ago, they brought the skull out, and they looked at the wounds, and they then by doing CAT scanning, they reestablished the path of the rod through Phineas's brain. And sure enough, it went through the frontal lobe. And that left frontal lobe was part of the executive function that he had, and his executive function was compromised by the destruction of the brain. Now, again, probably he recovered more function than we're willing to admit because it's such a great story. But in fact, this is a kind of inflection point, and we think about it in neurobiology as an important inflection point and how we think about the nervous system. Now, this is a story that actually recurred, about 10 years ago. And someone was going through a bunch of old photographic plates in an attic in New Bedford. And because New Bedford was an old whaling town, this picture went out, a copy of this picture went out on the internet, and it was captioned, "Whaler with Harpoon." Well, it didn't take very long before the aficionados on whaling out there looked at it and said, "That ain't no harpoon, and who ever heard of a one-eyed harpoonist anyway?" And when they looked more closely, they found that this rod actually had an inscription on it. And it was an inscription describing the accident. And what Phineas Gage was doing is he was going out to make a living, and shortly after his accident, he was going out making a living, going on a kind of circuit where he'd give talks about his accident. And he carried with him this tamping rod. But then later, after he died, this is what was sent back. And you can see there's a hole here, comes up through the back of his orbit of his eye, so his eye is blind in the left eye, and then the rod came out the top of his head. You can see this is rounded here, so it was a fair amount of healing. But this then took out a fair amount of Phineas's brain, and that's the beginning of saying the nervous system is just another machine. That is a remarkable machine, a remarkably delicate machine, but really a machine that tells us who we are and who we're going to be. So from there, what I want to do is talk a little bit about sensory transduction. And again, we can't get too far into the weeds on this. But I'll take this panel and describe it as sensory transduction. As a change in energy form. Specifically, we're going to change the energy so that the energy becomes transduced into ion movement across membranes. Now, in the world around us, there are three major kinds of energy that we use to figure out what's happening. The first is electromagnetic. The second is mechanical. And the third is chemical. And each of these transduction events is different in different animals and has some remarkable stories about it. Now, for us, the electromagnetic is vision. And the spectrum that we can see with our eyes, with our retinas, is from about 380 nanometers, wavelength of 380, to about 750 nanometers. Anything in this direction, where the wavelength is shorter, this now gets into the ultraviolet. And then as the wavelength gets shorter still, it gets down into X-rays, and finally gamma rays. As we move in this direction, the shorter and shorter the wavelength, each of those photons carries more energy. But we also can move in this direction. Once we get up above 750 nanometers, we're now into a region of infrared. And this is heat. And if we get longer, we can now get into radio waves. But we have this enormous electromagnetic spectrum that goes from fractions of a nanometer all the way up to tens of meters. So it's an enormous spectrum. And among that spectrum, all we are able to recognize is this narrow bit, which we call visible light. Now, the visible light that we see is red, orange, yellow, blue, sometimes it's called indigo, and violet. And then once we get down into the shorter wavelengths, we don't see it anymore. But that's not true for all animals. And some of you may have done this. If you get a modern camera that has a chip in it that's sensitive to ultraviolet light and go out to begin photographing flowers, you'll find these flowers have a whole new set of patterns to them. And the reason they have a whole new set of patterns is that there's certain pigments in those flowers that are reflecting ultraviolet light. And the reason those flowers are reflecting ultraviolet light is that there are pollinating insects that see well down into the ultraviolet. So the world to these pollinating insects looks very different than it does to us. And those flowers have evolved different patterns to attract these insects so that they can be pollinated by the insects. Another example I like of this is moving in the other direction. And that is as we move farther and farther into the infrared. Now, in our modern world, we have night vision goggles where we can actually see infrared. Put on the goggles and the machine basically converts the temperature into an image, and we can see in the infrared. But this is a relatively recent development in our world. If you put your phone away, I'd appreciate it. But in fact, there are animals who solved this problem long ago. And one of the classic solutions here are the pit vipers. And I don't know how many of you know about snakes, but all of the poisonous snakes in North America, except for the coral snake, are pit vipers. And the pit vipers are unique in that between their nose and their eye, there's this specialized region, which is a pit. In that pit, within the pit, there are all these sensory nerve endings that are receptive to heat. And they have been aggregated in this place on the face of these snakes. And those neurons then go back into the central nervous system. They go back into the brain. They go back into the integrative unit. And in certain regions in the integrative unit now, these animals can get an image of heat, much like the infrared glasses. And this is a real advantage if you're a snake hunting at night and your prey is a warm blood. So you go out at night and you find a mouse or a bird, and it has a signature to it. It's warm. But of course, the mouse or the bird can't see in the dark. But the snake can, and it can see the heat signature. And so it will go out and have dinner simply by using this specialized series of heat-sensitive neurons in its face, in the pit, to be able to recognize a form. It can get the direction of the mouse from that form. There are other animals that use different parts of the electromagnetic spectrum. There are migrating birds. The migrating birds recognize the Earth's electromagnetic field. Now, we can solve this problem with a compass. What the compass is reading is the electromagnetic field of the Earth. But these animals, particularly something like a homing pigeon, a homing pigeon is a remarkable animal. You can take this animal out 500-600 miles away from its home loft, throw it up in the air, and it will find its way home the same day. And it can do this in large part because it senses the electromagnetic field of the Earth. It has a built-in compass. I mean, I find this astonishing. I need a GPS to find the garage. So, yes. It's not clear. At one time, it was thought that between the eye and the beak, there was this little piece of iron, and that piece of iron was innervated. And recently, that hypothesis has begun to fall on bad times. And so they don't think that it's the piece of iron. They think it's something else. But at this point, they think it has to be some kind of ferrous metal, because that's the way we at least orient, that we need something that can orient in a magnetic field. So they're assuming it has to be a ferrous molecule that is now sending, through sensory transduction, is sending information to the brain. That's the best we can do. That's the last I heard on, at least a few years ago. The other one I find astonishing, and this is one that I have even less affinity with, and that is the sharks and rays. The sharks and rays will hunt by sensing the electromagnetic field of animals. Basically, we are a salt solution with ions. And when we move and we activate our nervous system, we slightly change the electromagnetic field that's generated by that salt solution and lipid bilayers. So we can't sense this very well because put your phone away to appreciate it. We can't sense this because we live in air, which is an insulating medium. But if you live in seawater, which is a conducting medium, these animals can recognize electromagnetic fields of animals. And so if you may have seen some of these images, they're really spectacular, where there's this ray, this beautiful ray with these great wings to it, sort of gliding along a few inches above the ocean bottom. Suddenly there's a flurry of activity and the ray has had dinner. What the ray has done is it sensed a fish buried in the sand by its electromagnetic signature. Recognized the electromagnetic signature and had dinner. The numbers in this are astonishing. The numbers that they can sense are microvolts per millimeter. And if you take the microvolts per millimeter out to kilometers, they can sense the voltage of a flashlight battery over like 1,000 kilometers. It's just an astonishing ability. But they actually use this. And you see over and over again, when there's selection pressures to have dinner, things will change. And that's with selection pressure here. Then mechanical is one we're all aware of. This is maybe the most intuitive one, because you can imagine reaching out and touching something. You can imagine there's sensory nerve endings in your fingers, and when you change the shape of the sensory nerve endings, that mechanical deformation, the mechanical energy can be changed to the movement of ions across membranes, initiate a signal that goes to the brain and begins this process of integration. So we can think about this fairly simply. We don't know exactly how all it gets done. We know how the mechanosensors are activated. We know how the signals are conducted. We know they get into the central nervous system. We can follow the pathway. But how they're integrated into an ability, for example, to get up in the morning, go grab your coffee filters, and recognize you have 2 filters rather than 1, and then start fumbling about so you put the one back and put the other in the coffee maker. How that gets done is completely a mystery. But that's all done by this mechanical thing. To me, the even more amazing one is hearing, because hearing is truly a mechanical sense. And as I'm standing here using my larynx, all I'm doing is taking those vocal folds, vibrating the vocal folds. Those vibrations now are being transmitted as compressions in the air and rarefied regions in the air. Those compressions now go out as a wave. Those compressions are picked up by your outer ear, funneled into the tympanic membrane, and through a series of small bones amplified a little bit. But they're still tiny vibrations. They're tiny vibrations of the tympanic membrane that are being transmitted to something known as endolymph. This is an ion solution. And there are cells in the ion solution called hair cells. And the hair cells are constructed in such a way that out of their apical surface, they have these cilia. These are called stereocilia. And the stereocilia appear to be connected by a kind of biological wire. And what will happen then is when this cilium moves a little bit and pulls on the wire, that now is amplified, so we open a channel here and ions come in. The movement of the cilium can be less than a few angstroms. Tiny, tiny movements generated by a mechanical movement in the endolymph, which starts the process of sensory transduction by, again, allowing ions to move through channels across a phospholipid bilayer. Over and over again, we see this theme. And then finally, there's chemical. And this is basically the chemical energy in the shapes of molecules is transduced to ion movements. Now we know these chemical senses as taste and smell. It's worth doing this experiment because it gives you a sense of how limited taste is and how remarkable smell is. And the experiment is to go out and buy a bag of jelly beans and close your eyes and reach into the bag of jelly beans. So without looking at the jelly bean, pop one of those jelly beans into your mouth, but hold your nose. If you hold your nose while you're chewing the jelly bean, it will taste sweet. Fair enough, because that's taste. There are 5 tastes. There is sweet and sour, bitter. Which one am I missing? Sweet, sour, bitter, umami. Salt. Sweet, sour, salt, bitter, and umami. And those 5 tastes are on your tongue. But now to get a proper flavor, in this case, the story of the jelly bean, to know whether that jelly bean was licorice or cinnamon or one of the other horrible artificial flavors, you have to let go of your nose. When you let go of your nose, now the aromatic molecules, the volatile molecules that you stirred up by chewing it, now go up into your nose. And now you have like, I think it's 1 billion or more different potential neurons to which these receptors, 1 billion or more receptors to which these odorant molecules can bind. And now it's the combination of the taste, sweet, and the odorants which give you flavor. And so it's that combination. And then all of that's interpreted in the central nervous system. So you really don't know the difference between taste and flavor until it's all sorted out by your brain. So you don't taste with your tongue, don't even taste with your nose, you taste with your brain. And so again, it's all of this goes back into the analytic parts of the brain to set up a response. Some of these taste and things are remarkable. Some of the early work was done on sensory transduction of odorants that moths use to be attracted to a mate. And if you've ever looked at a moth, they have these great, beautiful antennae they're just have very many branches to them. And what those branches do is they bind to molecules in the air. And these animals now can sense a gradient of these molecules in the air and work their way up the gradient to find a mate. And that's all done by having this, basically an odorant in the air binding to receptors in the antennae and signaling these animals which way to fly to find a mate. Again, something we can't really think about very clearly except through doing the experiments. But basically, what I want you to hold on to here is that we have three major ways of thinking about, of recognizing what's going on in the world around us. It either is electromagnetic, and different animals do this differently, it's mechanical, or it's chemical. Yes?
So when people have different tastes, more heightened or less, has nothing to do with their nose and their mouth, but purely their brain is better at understanding, translating the information.
So this is a question that came up last time too. So there are some individuals who have remarkable abilities for taste. And the wine tasters are a great example of this. And there's some wine tasters who can recognize the difference of a wine generated from a grape that's only a few hundred meters apart. And how this happens isn't all clear. Much of it has to be training. In some cases, people think that it's mostly training. Some people think that the difference between us and a bloodhound is simply, if you teach your nose to smell this, you can smell almost as well as a bloodhound can. But in the case of this tasting molecules, it's an interesting finding that many of the wine tasters, the world-class wine tasters, are what they call synesthetes. And a synesthete is someone who has a kind of overlap between the sensory modalities. And some of these wine tasters will describe a wine as being a red flash with two blue dots. So it's not only that they're tasting it, they do get the taste, but there's some additional kind of crosstalk between the olfactory and tasting system and the visual system, or maybe in some cases they'll hear something. And so these synesthetes have this overlapping sensory modalities. There have been a number of composers who also have this overlap, and their overlap is often between vision and sound. And so they think about sound as color. And in fact, even in most musicians will talk about sound as color. But these people will really hear a sound, and then they'll see a color. And then they can compose a piece by using this combination of sound and color, just as the wine taster can recognize a wine not just by its taste, but by the other sensory information that's elicited someplace up in the brain. So it's a very complicated, and it takes a lot of training to do that too. But anything else? Just a final point on this. Smell and taste, these chemical senses, are probably the oldest. Because if you think of animals swimming in a water column, they had to find something to eat. And so what they were doing is they were swimming up a gradient, usually of amino acids, of something decaying. And so they would find a pathway of decaying amino acids in the water column, follow it to its source. In the last couple minutes, let me start what we'll really spend more time on tomorrow. And this is the idea of the neuron doctrine. And I'll define it again here and try to describe the two diametrically opposed streams of thought, schools of thought that gave rise to it. The neuron doctrine says that the neuron is the fundamental, structural, and functional unit of the nervous system. Now, in the late part of the 19th century and the early part of the 20th century, this gave rise to two schools of thought. One school of thought were the cellularists. And these guys said the neurons are separate and distinct. They're separate and distinct cells. The other school of thought were the reticularists. And the reticularists said that every neuron is connected to every other neuron. by cytoplasmic bridges. Now, what the thought I want to leave you with is, and one of the major downfalls in this reasoning, was that if you have every cell connected to every other cell by a cytoplasmic bridge, how do you manage to get this directionality of information flow from the periphery to the central and back out again? And that was a real challenge they had to overcome and never did. So tomorrow I'll tell you how these two stories were sorted out.